There is a place in our universe where physics goes to die. It is not just empty space. It is a violent, silent hunger that sits at the center of galaxies. For 100 years, it lived only on paper. It was a ghost in our math, a terrifying error in general relativity that suggested gravity could become infinite. We tried to ignore the implications. We hoped the equations were wrong. Then, in the 1960s, the X-ray telescopes turned on, and we realized the monster was real. We call them black holes. They are the ultimate cosmic predator, eating stars and erasing history. We used to think of them as dead ends. Now we know they are the engines driving the cosmos. Today we are finally staring into the eye of the beast, and what we see is stranger than any fiction. Black holes are regions in space where gravity is so intense that nothing, not even light, can escape their grasp. The concept began to take shape in the early 20th century when Albert Einstein developed his general theory of relativity. Einstein's equations predicted that extremely dense masses could cause spacetime to curve so severely that a point of no return, or event horizon, would form. However, it wasn't until the 1960s that astronomers started identifying actual candidates, objects with incredible density and gravitational pull. John Wheeler popularized the term black hole, solidifying the idea in scientific circles. These mysterious objects challenged previous notions of space, time, and matter. Modern observations, such as the detection of gravitational waves and the imaging of a black hole's shadow, have confirmed that black holes are real, forging a new way to understand the universe's most extreme entities. Darkness itself hints at their presence, but there are more telltale signs than just an absence of light. One of the most striking clues is the existence of accretion disks, swirling spirals of gas and dust, hurtling toward a seemingly invisible point. As matter accelerates and heats up, it emits intense X-ray radiation, revealing the invisible beast lurking at the center of galaxies. Sometimes we observe stars orbiting a seemingly empty niche, moving at incredible speeds. Their rapid dance indicates a massive compact object exerting intense gravitational pull, too dense to be anything other than a black hole or a neutron star. Another phenomenon is the sudden powerful bursts of gamma rays or jets of high-energy particles shooting out at near-light speeds as matter is ejected from the vicinity of the black hole. These jets can stretch millions of light-years, creating cosmic lighthouses that pierce through the universe. Collectively, these signals paint a picture of objects that hide behind a veil of darkness, yet reveal themselves through their gravitational influence and energetic footprints. Black holes are not just mysterious cosmic vacuum cleaners. They are fundamental to our understanding of how the universe functions on the grandest scale. They serve as extreme laboratories where the laws of physics collide, general relativity and quantum mechanics pushing the boundaries of what we think is possible. Some scientists believe black holes act as cosmic seeds, influencing galaxy formation by drawing in vast clouds of gas and dust, shaping the large-scale structure of the universe. Their gravitational pull is so immense that they warp space-time itself, creating phenomena like gravitational waves that ripple through the cosmos, allowing us to learn about distant, otherwise invisible events. Many researchers see black holes as gateways to understanding the nature of space-time, gravity, and even the origins of the universe. In studying these enigmatic objects, we gain clues to some of the universe's deepest secrets, like whether the fabric of reality itself has limits, or if new physics awaits discovery beyond the event horizon. At the heart of a black hole lies the singularity, a point where gravity becomes infinitely strong and density skyrockets, where the normal rules of physics seem to break down. Surrounding this mysterious core is the event horizon, often called the point of no return. It's the boundary beyond which nothing, not even light, can escape the black hole's grasp. Just outside the event horizon, there's often an accretion disk, a swirling, glowing band of gas and dust spiraling inward, heated to extraordinary temperatures by intense friction. As matter accelerates towards the singularity, some of it gets channeled into powerful jets shooting out from the black hole's poles, blazing across space. These jets are like cosmic lighthouses, signaling the black hole's activity at enormous distances. Together, these components shape a black hole's structure, each playing a vital role in how it interacts with the universe. They make black holes not just destructive entities, but fascinating laboratories for physics at its most extreme. The event horizon is like the ultimate boundary of a black hole, the point beyond which nothing can escape, not even light. It's often called the point of no return, because once an object crosses it, it's inevitably pulled inward by the black hole's immense gravity. To imagine it, picture a sphere surrounding the black hole, marking the edge where gravitational pull becomes inescapable. This boundary isn't a physical surface, but a feature of spacetime itself. Its significance lies in the fact that it defines the black hole's invisible veil, separating the universe we observe from the mysterious depths within. Everything that slips past the event horizon is lost to the black hole's interior, where current physics break down. Understanding this boundary not only helps scientists grasp black holes' nature, but also provides insights into the fundamental fabric of space, time, and gravity itself. It's the gateway to unraveling the deepest secrets of our universe. Beyond the event horizon, the edge of no return, the universe takes a bizarre turn. Inside, the fabric of space and time warps so dramatically that our usual rules no longer apply. The laws of physics, as we understand them, start to break down. Matter gets pulled into an unimaginably dense point called a singularity, where gravity is so intense that it crushes everything to an infinite density and zero volume. Here, space and time converge into a strange singular point, a place where the equations governing our universe no longer hold. Some theories suggest that beyond the event horizon, the conventional understanding of reality simply ceases to exist. Others propose there might be tunnels or wormholes, connecting black holes to distant parts of the universe or even to other universes. While the inside remains a mystery, studying black holes pushes us to the very edges of physics, forcing us to rethink what's possible at the universe's most extreme limits. General relativity paints black holes as extreme warps in the fabric of spacetime caused by the concentration of mass and energy into an infinitely small point called a singularity. It explains that gravity isn't just a force pulling objects together, but a curvature in spacetime itself. Massive objects like stars deform spacetime around them, and when a star exhausts its fuel and collapses under its own gravity, this deformation intensifies dramatically. As the collapse continues, spacetime warps so severely that nothing, not even light, can escape once it crosses the event horizon. This boundary marks the point of no return. According to Einstein's theory, the singularity at the core is a place where density becomes infinite, and the laws of physics as we know them break down. Yet, general relativity gracefully describes the dynamics leading up to this point, shedding light on how mass and energy influence the universe's geometry in astonishingly extreme environments. Quantum mechanics is where the mystery deepens. While Einstein's theory of general relativity beautifully describes the massive gravitational aspects of black holes, it doesn't quite tell the whole story at the tiniest scales. Inside a black hole, where gravity becomes infinitely strong at the singularity, quantum effects start to matter profoundly. This is where physicists believe the rules of the universe, quantum mechanics, must be woven into the fabric of space-time itself. One of the biggest puzzles is how information behaves near or inside a black hole. According to quantum mechanics, information can't just disappear, but if something falls into a black hole, classical theory suggests it might be lost forever, challenging fundamental principles. Scientists are working tirelessly to reconcile these conflicting ideas through theories like quantum gravity and holography. These efforts aim to reveal whether black holes act as cosmic encryptors or secrets keepers, holding clues to unify the very small with the very large. Hawking radiation is a fascinating quantum phenomenon where black holes aren't completely black after all. Imagine the vacuum of space isn't entirely empty but teeming with pairs of particles popping in and out of existence. Near the event horizon of a black hole, sometimes one particle falls in while the other escapes, carrying energy away from the black hole. Over vast periods, this process causes the black hole to slowly lose mass and eventually evaporate completely. This discovery by Stephen Hawking shattered the idea that nothing could escape a black hole's grasp. It also raises profound questions about the fate of information swallowed by black holes, challenging our understanding of physics. Hawking radiation implies that black holes are not eternal, they have a lifespan that depends on their size. This insight bridges quantum mechanics, gravity, and thermodynamics, pushing scientists toward a unified theory of everything, one that can explain how the universe's deepest mysteries fit together. Recently, scientists have developed some incredible techniques to peer deeper into black holes than ever before. One of the groundbreaking methods is very long baseline interferometry, or VLBI, which connects radio telescopes across the globe to create a virtual Earth-sized telescope. This technique allowed the Event Horizon Telescope collaboration to capture the first direct image of a black hole's shadow in the galaxy M87. By analyzing this shadow, astronomers can learn about the black hole's size, shape, and the behavior of matter at the edge of the event horizon. Meanwhile, gravitational wave detectors like LIGO and Virgo have revolutionized our understanding by capturing ripples in spacetime caused by black hole mergers. These waves provide clues about black hole masses, spins, and even their population across the universe. Additionally, X-ray observatories sense high-energy emissions from hot accretion disks, revealing insights into how black holes consume matter. With each new observation, we're peeling back more layers of these cosmic mysteries. The arrival of groundbreaking observations like the Event Horizon Telescope has revolutionized our view of black holes. For the first time, we captured an image of a black hole's shadow, revealing a bright ring of hot plasma swirling around an invisible boundary. This visual confirmation of the Event Horizon's silhouette validates decades of theoretical predictions and provides concrete evidence that these cosmic giants behave as Einstein's equations suggest. It turns what used to be purely mathematical models into tangible, observable phenomena. These images also help us understand the environment near the event horizon, shedding light on how matter interacts with extreme gravity. Moreover, they stimulate new questions about the nature of spacetime and quantum effects at the edge of black holes. The ability to directly observe these objects bridges the gap between theory and reality, transforming black holes from distant, mysterious objects into accessible laboratories where fundamental physics unfolds before our eyes. Recently, scientists have made some astonishing strides in unraveling the mysteries of black holes. One of the biggest breakthroughs came in 2019 when the Event Horizon Telescope captured the first ever image of a black hole's shadow in the galaxy M87. This monumental achievement provided direct visual evidence of what the event horizon looks like and confirmed many predictions made by Einstein's theory. Alongside this, researchers have detected gravitational waves from black hole mergers more frequently and with greater clarity, opening a new window into their populations and behaviors across the universe. These observations have helped refine our understanding of how black holes grow and interact with their surroundings. Additionally, advancements in theoretical physics have led to the development of new models, blending quantum mechanics with gravity, bringing us closer to a quantum theory of gravity. Such progress fuels the hope that someday we'll fully comprehend the interior of black holes and what truly lies beyond the event horizon. Scientists have long wrestled with the mystery of what lies beyond the event horizon. One leading idea is that the singularity at the core represents a point where gravity becomes infinitely intense, crushing matter into a state beyond our understanding. According to Einstein's general relativity, this is where the laws of physics as we know them break down, leaving us with a puzzle rather than a clear picture. Some theories propose that instead of a traditional singularity, there could be a portal or wormhole, a shortcut through space-time, potentially connecting to distant parts of the universe or even other universes. Others suggest that quantum mechanics might play a vital role, perhaps smoothing out the infinite densities and preventing a true singularity from forming. In this view, black holes could be cosmic storage units, with information preserved in some way, challenging our notions of what it means for something to be lost forever. The ongoing quest is to reconcile these contrasting ideas into a coherent picture that agrees with both relativity and quantum physics. One of the biggest questions scientists grapple with is whether information falling into a black hole is lost forever or somehow preserved. According to classical physics, Once something crosses the event horizon, it's gone from our universe, seemingly destroyed at the singularity. But quantum mechanics throws a wrench into that idea, suggesting that information can't just vanish, it must be conserved. This paradox, known as the black hole information paradox, has puzzled physicists for decades. Recent theories propose that information might be encoded on the event horizon itself, a concept called the holographic principle. This would mean that instead of disappearing, the information is somehow stored on the surface of the black hole. As the black hole radiates Hawking radiation and slowly evaporates, it could release that information back into space. If this is true, it would bridge the gap between general relativity and quantum mechanics, hinting at a deeper, unified understanding of reality. The mystery is far from solved, but each discovery gets us closer to the truth. Singularity is where the fabric of spacetime curves infinitely, and the laws of physics as we know them seem to break down. It's like trying to understand a story with a page torn in the middle. Our equations hit a wall. At a singularity, density becomes infinite, and the gravitational pull is so intense that space and time lose their meaning. This suggests that our current theories, Einstein's general relativity and quantum mechanics, don't quite fit together in these extremes. The paradox lies in how gravity can be so powerful, yet coexist with the strange probabilistic world of quantum physics. Some scientists wonder if singularities are actual physical entities, or just signs that our understanding is incomplete. These cosmic enigmas push us to develop new theories, perhaps quantum gravity, that can merge gravity with quantum mechanics, giving us a clearer picture of what happens at the heart of a black hole. Until then, the singularity remains a tantalizing mystery that challenges the limits of physics itself. The black hole information paradox is one of the biggest puzzles in modern physics. It arises from the clash between quantum mechanics and Einstein's theory of gravity. Quantum physics tells us that information about a physical system, like the details of how objects form or change, must always be preserved. But when something falls into a black hole, classical physics suggests that all that information is lost once it crosses the event horizon. This raises a shocking question. Does the information simply evaporate or disappear? If so, it breaks the rules of quantum mechanics, which insists that information can never be destroyed. Stephen Hawking famously showed that black holes can slowly evaporate through a process called Hawking radiation. As they do, what happens to the information? Does it hide forever in the black hole's interior? Or is there a way for it to escape, perhaps encoded in the radiation? Solving this paradox isn't just about black holes. It's about understanding the very fabric of reality and uniting the principles that govern the universe at its most fundamental level. Scientists have been racing to resolve the black hole information paradox for decades. One leading idea is the concept of holography, which suggests that all the information swallowed by a black hole is somehow encoded on its event horizon, like a cosmic hologram. This means that the information isn't lost, but rather stored on a two-dimensional surface, preserving the laws of quantum mechanics. Then there's the firewall hypothesis, proposing that a fiery barrier exists at the event horizon, burning up anything that tries to pass through, and thus altering our understanding of what happens at the edge of a black hole. Another intriguing approach involves the possibility that black holes might be connected through wormholes or Einstein-Rosen bridges, potentially allowing information to escape in a way that preserves the universe's fundamental rules. Additionally, some theories suggest that the true resolution might require a complete theory of quantum gravity, a yet-to-be-formulated framework that combines Einstein's relativity with quantum mechanics. These ideas are still unfolding, but they're bringing us closer to deciphering what really happens inside these cosmic giants. Scientists are actively working to test the bold theories about what happens inside black holes, though many remain challenging to verify directly. One promising approach involves detecting gravitational waves, ripples in spacetime caused by violent cosmic events like black hole mergers. These waves carry signatures that might hint at unusual phenomena near the event horizon or inside the singularity, offering clues about the true nature of black holes. Additionally, researchers are exploring how particles and light behave close to the event horizon, using telescopes like the Event Horizon Telescope, which captured the first image of a black hole's shadow. Future missions aim to study black hole jets and accretion disks in greater detail, searching for deviations from Einstein's predictions. Theoretical experiments also play a role. Simulating black hole conditions in particle accelerators or quantum labs could provide insights into phenomena like Hawking radiation or the information paradox, bringing us closer to understanding these cosmic enigmas. Absolutely. The idea of a singularity at the core of a black hole has long troubled scientists, sparking numerous alternative models that aim to bypass this infinite density nightmare. Some theories suggest that what we perceive as a singularity is actually a region of extreme but finite density, sometimes called a Planck star or a fuzzball, where quantum effects prevent true divergence. Loop quantum gravity, for instance, proposes that space itself is quantized, preventing the formation of a singularity by replacing it with a highly dense but non-diverging core. Similarly, string theory offers models where the collapsing matter transforms into a tangled web of fundamental strings, smearing out what would otherwise be a point of infinite density. These models don't just aim to solve the mathematical infinities, they also impact how information might escape or be preserved inside black holes, bringing us closer to understanding the true nature of these cosmic mysteries. The journey to unravel what lies beyond the event horizon continues, full of exciting possibilities. The idea that the interior of a black hole might connect to other universes or dimensions has captivated scientists and science fiction enthusiasts alike. Some theories in physics, like the concept of a wormhole, suggest that black holes could serve as cosmic tunnels, gateways bridging distant parts of our universe or even different universes altogether. These hypothetical bridges are thought to occur in solutions to Einstein's equations, offering a potential shortcut through spacetime. But here's the tricky part. Inside the black hole, our understanding of physics breaks down at the singularity, the point where density becomes infinite. It's like trying to puzzle out the workings of a clock when the gears have melted away. While these ideas are tantalizing, they remain purely speculative without experimental evidence. Still, they fuel ongoing research, pushing us to think beyond the limits of our universe. Could black holes be cosmic portals? It's one of the most fascinating questions still waiting to be answered. The idea of a firewall is one of the most mind-bending puzzles in black hole physics. According to some theories, as an object approaches the event horizon, a fiery wall of energy could suddenly ignite, incinerating anything that tries to pass through. This concept was proposed to resolve a paradox called the black hole information paradox, which questions whether information that falls into a black hole is lost forever or somehow preserved. The firewall suggests that at the edge of the black hole, the fabric of space might become a blazing inferno, contradicting Einstein's idea that the event horizon is just a smooth crossing point. But here's where things get messy. Many physicists find the firewall idea deeply unsettling. It challenges the principle of equivalence, which states that crossing the event horizon shouldn't be locally distinguishable from floating in empty space. If firewall theories are correct, then the very nature of reality near a black hole shifts dramatically. The debate rages on, highlighting just how much we still have to learn about these cosmic mysteries. Black holes are not just cosmic vacuum cleaners, they are powerful engines shaping the very fabric of their galaxies. Supermassive black holes, often millions or billions of times more massive than our Sun, sit at the centers of most galaxies, including our own Milky Way. Their gravitational pull helps organize the motion of stars and gas, influencing galaxy structure. But it's not just gravity at play. When material falls into a black hole, it heats up and emits energetic jets and radiation. These outflows can sweep through the galaxy, regulating star formation by either triggering it in some regions or quenching it in others. This delicate balance can determine whether a galaxy grows lush with new stars or becomes a barren, aging system. So black holes act as cosmic thermostats, controlling the pace of galaxy evolution. Their influence stretches across cosmic scales, connecting the fate of individual black holes to the grand story of how galaxies form, grow, and change over billions of years. Understanding black holes offers a window into the ultimate destiny of the universe itself. These cosmic giants, with their intense gravity and mysterious event horizons, challenge our understanding of physics and hint at what lies beyond. When we explore what happens inside black holes, especially near the singularity, we confront questions about the nature of space, time, and matter at their most extreme. Some theories suggest that black holes could be gateways or portals to other parts of the cosmos, or even alternate universes, stirring speculation about multiverses. Others propose they might eventually evaporate through Hawking radiation, slowly shrinking and crumbling away over unimaginable timescales. The fate of black holes, then, is intertwined with the evolution of the universe, influencing how galaxies grow, how the cosmos expands, and whether it will end in a big freeze, big rip, or big crunch. Each discovery about black holes gets us closer to understanding how the universe might end, or if it has an end at all. Future discoveries about black holes have the potential to revolutionize our understanding of the universe and the fundamental laws that govern it. As we unlock more about what happens at the boundary of the event horizon and potentially inside the singularity, we could find clues that bridge the gap between quantum mechanics and general relativity, two pillars of physics that currently clash at these extreme environments. Imagine a breakthrough revealing how gravity operates at the smallest scales, or how information is preserved in black hole interactions. Such insights might lead us to formulate a unified theory of everything, possibly solving age-old puzzles like the nature of dark matter and dark energy. Moreover, understanding black holes better could inspire new technologies and experimental methods, opening windows into previously inaccessible realms of physics. We might even uncover new states of matter or energy, rewriting textbooks and sparking a new era of scientific discovery. The mysteries inside black holes may hold the keys to unlocking the universe's deepest secrets. One of the biggest mysteries still surrounding black holes is what truly happens at the very core, the singularity. Current physics suggests infinite density and curvature, but that idea doesn't sit well with quantum mechanics, which demands a more refined explanation. Do black holes have a boundary where known laws break down entirely, or is there a way for this breakdown to be avoided? The phenomenon known as the information paradox adds another twist. How does information about matter that falls into a black hole get preserved, if at all? Many scientists speculate about possibilities like firewalls or other exotic physics that might resolve this paradox. Then there's the tantalizing idea of wormholes, hypothetical tunnels connecting distant parts of the universe, or even different universes. Could black holes be gateways to these cosmic shortcuts? And what about the true nature of the event horizon itself? Could it be more than just a point of no return? These questions keep pushing the boundaries of our understanding, hinting at deeper secrets woven into the fabric of spacetime. Advancements in technology are poised to revolutionize our understanding of black holes in ways we can't yet imagine. As telescopes become more powerful, capable of capturing unprecedented details of the event horizon and surrounding spacetime, we'll be able to peer deeper into the mysteries of these cosmic giants. Quantum sensors and gravitational wave detectors will improve sensitivity, allowing us to observe black hole mergers and their echoes with greater precision, revealing clues about their inner workings. Computational power will enable us to run more sophisticated simulations, testing theories like quantum gravity and the nature of singularities. Future missions might even send probes close enough to explore black hole environments directly, pushing the boundaries of human reach. With each technological leap, we edge closer to uncovering whether black holes are simply cosmic vacuum cleaners or gateways to entirely new realms of physics. Every breakthrough will sharpen our insights, helping decode the secrets of the universe's most enigmatic objects. The revelations about what lies inside black holes challenge our very understanding of reality and our place in the universe. If singularities truly exist at the heart of these cosmic monsters, they defy the laws of physics, forcing us to confront the limits of human knowledge. The idea that information might be destroyed or preserved as it crosses the event horizon sparks debates about the nature of truth and whether the universe itself is fundamentally deterministic. Black holes also raise questions about the fabric of spacetime. Does space and time break down at the singularity, or is there something beyond our current comprehension? These mysteries provoke us to reconsider concepts like causality, free will, and the interconnectedness of everything. As we probe deeper into these enigmas, black holes become more than astrophysical phenomena. They become mirrors reflecting the deepest questions about existence, consciousness, and the ultimate nature of reality itself.